Okay, so this is just a continuation of the probability talk we had before. This kind of assumes you know what an expected value is of a random variable, what the variance is of a random variable, and therefore what the standard deviation. So the expected value is what the average of the events would average out to, and a standard deviation was how far you expect a random event to be away from the expected value. Okay. And so now we just want to cover more advanced topics, which might be like if we're looking at two stocks. And if the two stocks are somehow connected to each other. So kind of the motivation for this, or how this part of probability theory maps into financial mathematics, might be like, let's say you had two stocks, like Coke and Pepsi. And you notice the pattern, and when Coke goes up, Pepsi goes up too. Or maybe when Coke goes up, Pepsi goes down, because they're the only two in the market. So maybe you've noticed some kind of pattern you're trying to look for when they're correlated to each other. Or the other case would be if two events are happening maybe independent of each other, but then you start to notice if you have information about one, it gives you more information about another. So again, this is like a mathematical review, but we're going to plug these concepts into financial mathematics. So a conditional probability, the conditional probability that E occurs given that F has occurred already is denoted like this. We say the probability of E given that we know that the outcome of F was already F. So if the probability of F is anything bigger than 0, then the probability of having E happen, knowing that F has already happened, is really equal to the probability of E times F divided by the probability of F. So you could think of this as a two-dimensional variable, E and F, and then under a three-dimensional, a dome type thing, we have the volume adds up to 1. Instead of being the area under the code, the area adding up to 1 for a probability distribution with two variables, it would be a three-dimensional field, and its volume would add up to 1. And then we just use double integrals to add up the space under them. Okay, so try to go over some simple examples. So suppose we had an example where you're rolling two dice, and I'm going to say one of the dice is red and one is green. Is dice, would you say die or dice? I'm not sure I'm saying it right, but is it red die and a green die?
Yes.
Okay.
I think so.
D-I, it's spelled?
D-I-E.
D-I-E?
Actually.
Okay.
Dice.
Okay, but anyway, you kind of get the idea. So if you roll two dice can go, the total can be anywhere from 2 to 12. And the probability of getting a 2, you'd have to get a 1 on the red dice and a 1 on the green dice. That would be 1 out of 36. The probability of getting a 3, there's two ways you can do it. The red dice could be 1 and the green dice could be 2, or the red dice could be 2 and the green dice could be 1. So there's two ways. And of all the different combinations with using red and green, the reason I said they have a color is so I can say, like, the left one or the right one. So there's different combinations of them as you get closer and closer to what ends up being the expected value, which is 7. There's 2 out of 36 ways to get a 3 with two dice. And then to get a 4 would be a 1 and a 3 and a 1, and 2 2s. There's 3 ways to do it. So it would be 3 out of 36 for a 4. This pattern would go on until you get up to 7, which is the most common number. There's 6 different ways to do it. And then we'll start counting backwards back down to 1/36. Okay. So that's an example of just, so in this case now, we have one event. The one event is the total of the two dice. But we could kind of think of it as two different events going on independent of each other, and then we add them together. Right? So really it's one event, but it's really composed of two events. Now if you start taking stock, you buy two different stocks, and you want to know what is the total amount of money you have. It's really a combination of two different events that may be correlated to each other or maybe not correlated to each other. But something like this will happen. We'll have two different events, and our total is our overarching event. So suppose you were asked a question, like, what is the expected value of this? Would be 7. Actually, it would probably be a big computation. I'd have to say 1 out of 36 times 2 plus 2 out of 36 times 3, and sum it all up, and that would come out to 7. Now, what is the probability distribution of the total given? Now I'm going to give you a piece of inside information. If I say the green dice came out 3, now what is the probability distribution? The thing from before, the chance of a 2 is now impossible for the total to be 2 if one of the dice is already 3. So with this piece of information, the green dice turned out to be a 3. That changes the probability distribution for the total to be, it can only be 4 through 9, right, depending on the red dice. And now it's back to 1, 6, 1, 6, 1, 6, going 4 through 9. Couldn't possibly be 10, because 3 plus the red dice could never reach 10. There's no 7 on the dice. So as soon as you're given one piece of information, if we have 2 different events being added together to come up with a third event, and you're given information about one of the 2 composition events, then it would change the distribution for the event we're looking at. So that's a conditional probability, where you know one component of your overall event that would then change other events. So in that example, the red dice and the green dice are independent of each other. There's no connection between the 2. They roll randomly. So let's say, here's another example for playing cards. If I ask in a 52 card, a normal 52 card playing card deck, what is the probability of picking out an ace? So there's 4 aces in the deck, and there's 52 cards. It'll be 4 out of 52, which is 1 out of 13. Now, if somebody took a jack out of the deck, and you take the remaining 51 cards, now what's the probability you'll get an ace? That would end up being 4 out of 51 cards. So that piece of information you just got, a jack is missing, changes the probability of your question. So now it's not just like 2 dice being rolled together. Pretty much any piece of information you know about your event, given that you now know this piece of information, what's the new probability distribution? It would turn into 4 out of 51, because a jack is a non-ace. Now suppose we get back to the original deck, and you're told that somebody has removed a card, and the card is a spade. Might be an ace or it might not be an ace, but somebody pulled out a card and you're told it's a spade. Now what's the probability that you can pick out an ace? That information doesn't really change the question. Could be the ace of spades, or it could be some other spade, but you don't know. So with that piece of information, your original question remains unchanged. So that piece of information is independent of the original question. So the answer ends up staying, in that case, would end up staying 1 out of 13, just like before. So what we're conditioning on doesn't have to be like the 2 dice. It could just be any piece of information you're given about the event. Sometimes the information you're given doesn't change what you expect to happen, and sometimes it will. You could use that information to get a different probability distribution. Okay. Now, a joint cumulative distribution would be, we would say, okay, so basically suppose we had a function f of 2 variables, x and y. So maybe you remember this from mathematics, like z equals a function of x and y. So there would be a surface that the volume under the surface, if it's a joint probability distribution, would have a volume of 1. And then you could say, what is the probability that one variable is less than a and another one is less than b? You would integrate from negative infinity up to a for the x variable, and then integrate from negative infinity up to b for the y variable, and whatever that added up to, that's the probability that you picked a place between negative infinity in a and negative infinity in b. So this is once again, like if the information you start off with is the distribution is a combination of two other events, kind of like what is the total of two dice, right? So it's really made up of two separate events that are being added together. So if you wanted to know the probability distribution of just X, that is like we had in what we talked about last time when we talked about probability, was the probability that X is less than A. That ends up being the probability that X is less than A, given that Y is less than positive infinity, which means the same as saying that X is less than A. And then if we take the limit as B goes to infinity, so we're plugging in a B here instead of infinity. This is just another way of stating this line. And then in this line, we're just moving the limit outside of the probability, because it doesn't affect the probability part of it. And then the probability that X is less than A, given that Y is less than B, is equal to the limit as B goes to infinity of f of A and B, which is really f of A, and plugging in infinity for B. So it's really the original function just plugging in an infinity into B will tell us the probability distribution for A alone. So this less than or equal to part, this is like when, usually that's done in the continuous case where you're going from negative infinity up to a certain number. So if you wanted to know, like, if you wanted to map this to the discrete case with the example with the two dice, it would be like saying Y is equal to 6, what is the probability distribution for X? That the total would be less than 36, then that would give you the 1/6 of every number for the red, the red dice in that case. So this is where you're given the thing you're given is joint between two separate events. And we wanted to ask ourselves, what does it look like just from one of the events alone? So like I said, an example of two events being put together is like you start off with the total of two dice, and then you started to want to analyze what does each dice look like separately. You can get from the joint distribution, you can get the individual distributions. Okay. So here's a continuous case version of this problem. And I don't know if this will come out, so I'll read it. So a market buy order and a market sell order arrive uniformly distributed between 1 and 2 p.m. Each person puts a 10-minute time limit on their order. So what that means is somebody says, I want to buy at market, right? You put in a market order. But you say, if this order is not fulfilled in 10 minutes, then take it down. And another person wants to put in a sell order, and same rules. If 10 minutes later no person lines up with me, then take it down. So now the question is, what is the probability that the trade will not be executed due to a timeout? Right, so does the question make sense? So between 1 o'clock and 2 o'clock, two things are going to happen at a random point in time, uniformly distributed, so it could be, the probability of being anywhere is all equal to each other. And then the question is, what is the probability that the two events are more than 10 minutes apart? So if the buy order came in at 10 after 1 and the sell order came in at 1:30, they would not line up because the buy order would go away before the sell order came in. So no deal would go through. But if one came in at 1:38 and the other one came in at 1:46, they would be 8 minutes apart. So then it would go through. Right, so the question is, what is the probability that the gap of time between these two random variables would be greater than 10? If it's greater than 10, the deal doesn't go through. So what we're really doing is we're taking the F is the 0 to 60 of both of them being multiplied together. So really the F in this case is 1/60th squared. And then we could add up the times for the buy order and the sell order. and then just ask ourselves, you know, doing this double integral, we can find out what is the area where the two of them are more than 10 minutes apart from each other. So this would be the probability that B, the time the buy order came in, B plus 10 is less than the sell time, plus the probability that the sell order plus 10 is less than the buy time. Which is really, it's now for symmetry reasons, we can just say 2 times either one of those would work. These would be perfectly symmetrical to each other. So then we would say 2 times the double integral from B plus 10, as long as B plus 10 is less than S, of our 1 divided by 60 squared, and then dB ds, the 2 variables of integration. These would then separate, like we showed from the previous slide, into the f of b and this should be an s. Yeah, this should be an s. Okay. So the f of big B, little b, f of big S, little s, dB ds. Oh, we should reverse those two. On the interval from when b plus 10 is less than s. That would mean they're more than 10 minutes apart. This means they're more than 10 minutes apart and B came first. And then I'm multiplying it by 2 for the S came first version. So this would end up being, we'd be integrating from 10 to 60, and then from 0 up to S minus 10. And our F function, which is 1/60th, because it's 60 minutes for each of these, 1/60th squared would be our F function. And then if we integrated this, we get 2 times 1/60th to the minus, we integrated, so go up. So we end up with this 2, and then 1/60th, and then we have this outer integral from 10 to 60 of I should have put more steps in here, because this ends up being, when we plug in 0 to S minus 10, it should be an S. Sorry about this. Let me make this change now. I think it's a little confusing. I was thinking X and Y, and okay,
X.
this one, right?
Up one. The F. Should be F, S.
Which one?
You gotta go up one.
This one?
Yeah.
Oh, right,
The
okay.
little X.
This one. Okay.
No. The F of X.
Yeah.
In the middle
Oh,
of the
this
equation.
thing.
There you go.
It's a capital S, okay. Okay. So hopefully that's a little bit clearer. So I was thinking of the example, I'm always thinking X and Y, and then I put in buy and sell, so I just want to make sure they all lined up right. Okay, so then we end up, after we clean this up, we have the integral from 10 to 60 of what we got from the last integration. And then this ends up being 25 out of 36. That's the probability that the times between the two would be more than 10 minutes apart. Okay, so that, I mean, this was just an example of where you have you have kind of a natural situation where there are 2 components that make up our probability distribution. It's 2 random events, a buy order and a sell order, which we don't have control over. And then the problem is, if you do the buy minus the sell, how much time between them is what our random variable is. Could be 12 minutes apart, could be 8 minutes apart, could be 52 minutes apart. and we're trying to capture the gap of time between them. Okay. So, again, this would be a cumulative distribution between two variables. So now the question is, if you had an event like this, two different things going on at once that are being either, they don't have to be added together like the two dice, they could be just some connection between the two, like how much time is between them. But if we wanted to now figure out what is the expected value of joint distributions, so we'd have a function like f. This could be how much time each one takes, what time these things happen, and how much time is between them, or add the two numbers together, subtract the two numbers together. Anything you can do with those. But if we now said, okay, we have this event, f of x and y, and now I want to say, what is the expected value of, I'm going to take the x component and do something with it, and the y component and do something else, some function h, and operate on that. So we could take, it's basically the probability that the thing will happen times the amount of the event. So this is just the two-dimensional version of the expected value. And we integrate all the way from the lowest possible value to the highest possible value. So this thing ends up, we can break this into the x component and the y component. Then we can take the x component and move it over to the g and the x, put those together, and the h and the y, put those together. Since they would then integrate independently of each other, we can separate the integral sign. And we end up getting just the expected value of h of y times the expected value of g of x. So this would be whether they were independent of each other or not. And then this is a new statistic which will, a new statistic that captures a connection between two different random variables. So we'll call this the covariance of two random variables. The covariance is going to be equal to, we'll say, the expected value of the random x component of the event minus the expected value of x times a random run of y minus the expected value of y, and multiply those two together. So now we just do some math on the expected value of x and y minus the expected value of x, the expected value of x times y, minus the expected value of x times the expected value of y, plus the expected value of x times the expected value of y. The two minus signs cancel each other and made a plus. Then a little bit of a cleanup, we can see that y is equal to, the expected value of y is what we would expect y to be, so we can replace y with the expected value of y. Same thing here, this x can be replaced with the expected value of x. These two stay the same and the first two stay the same. So now we have the expected value of x times y minus this, minus another copy, and then plus a copy. So it ends up being the expected value of x and y minus the expected value of x times the expected value of y. So this is going to be a statistic we'll call the covariance of two random variables. Now the thing is this, if x and y are totally independent of each other, let's say like the red dice and the green dice, the expected value of x times y and the expected value of x times the expected value of y would be the same. Right? It's not like, so if one of the dice for some reason, let's say there was something strange about the dice, that if one was high, the other one would go low. Let's say there was a connection between the two. Like if the red one came out a 6, the green one would come out like a 1 or a 2 very often. It wasn't completely random. Then this thing and this thing might not equal each other. But if they're just totally independent, we would expect taking x times y and figuring out what do we expect that to be, and then taking what we expect x to be and multiply that by what we expect y to be, would come out the same. So if x and y are independent, then the covariance will equal 0. So if we found ourselves in a situation where we had, and actually one thing I want to point out, it is possible for the covariance to be 0, and yet x and y could be, in a small way, dependent on each other. But this covariance will give us an idea of how much these two variables are connected to each other. So if the two of them varied together, like a high x would usually mean a high y, then which of these two terms would you expect to be greater? See, the expected value of x would just be a random version of x and a random version of y. If we said that x and y were correlated to each other. Let's say, for example, I'll think of an extreme case. Suppose x and y are the same thing. Suppose we just had a red dice and we rolled it, and we call that event 1 and event 2. And we took the total of those two events. So if you roll a 6, the total is 36. If you roll a 1, the total is 2. So that means x and y are very correlated. When one is high, the other one's also high too. When one is low, the other one's low. What would you expect? Which one of these terms would you expect to be higher than the other? So this would end up being every combination there is. 6 times 1, 6 times 2, 5 times 3, every possible combination. This would be either 6 times 6, or 5 times 5, or 4 times 4. This would be the average of 36, 25, 16. And this would be the average of, like, 3.5 times 3.5. It'd probably be in the order of, this would be around 10 or 11. This would end up being a little bit higher because they're correlated to each other. So this ends up being a statistic that we can use to show how much the two events are connected to each other or not connected to each other. Okay, now this is a different topic. Sometimes I get confused and I get these two to overlap with each other, but this is a different topic. So remember we talked about the variance of a random variable. That was basically, the variance was the square of the standard deviation. It's how far we expect it to be away from the mean squared, right? And that always ended up being a positive number, and if you remember, if it was 0, it means there's no varying at all. We keep hitting the same result every time. Now suppose you had two random variables that you were adding them together. Again, like two dice, and just take their total and add them together. What would the variance of two dice be? Well, one way we could do it is we could just take the total of the two dice, 2 through 12, the possible outcomes, what are the probabilities of hitting them. The expected value in that case would be 7. And then we'd say, on average, of all the things we could get, how often do they come up and how far away are they from 7? And then take a running average. That would be the variance. And then the square root of that would be the standard deviation. But if we knew that rolling two dice and asking what is the total, we could just take the variance of the two individual dice and then use this dice, the individual die, and then use this formula, and that would be another way to calculate the variance. So the variance of two random variables is equal to the expected value of the two random variables. So that would be like we've done before. Remember, the regular variance of one random variable was the expected value, the event, the random variable minus the expected value of the random variable, and then take that whole thing and square it. So now what is the new event? The new event is the two events added together, right? Because we're saying what is the variance of the sum of two random variables. So the two events added together, then take what we expect x plus y to be and subtract that. Then take the whole thing and square it. So we just reuse the same formula from before. It's just the new event is now, it's not x. Last time it was x minus e of x, the whole thing squared. Now the event is x plus y minus e of x plus y, and the whole thing squared. So now we go and we say, all right, now we just crank through the math to get an easier to read explanation. So we have the expected value of x plus y minus, and this is just a notation ex. You see this sometimes in textbooks. This one's the expected value of x. So it's the expected value of x minus the expected value of y, and the whole thing all squared. So basically, I just distributed that minus sign through here, and used this notation ex, meaning expected value of x. So now we have the expected value of x minus the expected value of x. I'm just taking this and moving it over, like swapping these two, plus y minus the expected value of y, the whole thing squared, equals, now I'm distributing the squares. So the expected value of x, I'm sorry, it's the expected value of, and then everything on the inside is x minus the expected value of x, that squared, y minus the expected value of y, that part squared, and then 2 times x minus the expected value of x times y minus the expected value of y. And a little bit more cleanup. This won't fit on one line, but anyway, this ends up being a more cleaned up version of it. The expected value of x, I'm sorry, x minus the expected value of x squared plus y minus the expected value of y squared plus 2 times the expected value of x minus the expected value of x times y minus the expected value of y. And that's like saying the original thing, the variance of x plus y equals this now, this part is our original variance of the independent variable x. This is the variance of the variable y by itself. And this right here is what we defined last slide to be the covariance. So 2 times the covariance is what the variance of x and y is. So covariance, unfortunately they both have variance in their name, so you start to get those, I get those confused. But the covariance, which we defined on the last slide, is a measure of the connection between the two variables. 0 would mean they're either not connected or the connection is very weak, and if it got higher, then there would be a strong connection between them. So if they were independent, meaning no connection, what would this term be? The covariance would be 0 if they're independent, right? So this term would be gone. So what is the variance of 2 random variables that are completely independent of each other, like 2 dice, a red dice and a green dice? What would their variance be? Their variance would be the variance of the red dice and the variance of the green dice. So I think I remember the variance of a dice was it 2.92, and then we took the square root of it? I forget what it was, so it probably came out to 1.4 or something like that. So the variance of 2 dice being added together would be whatever that is, 1.4 times 2. So we have 2 different ways of drawing the variance. If they are dependent, if there's a connection between the 2 events, then there'd be another component added to, and this would be a positive number. This would be added to the variance of our variable. Okay. Then we want to come up with another statistic that, you know, the bigger it gets, the more correlated they are to each other. So there's this idea of a correlation between 2 random variables. So we'd like to have a statistic that would come out 0 if they're not related to each other, and then would grow in magnitude depending on how much they are related to each other. So as long as the variance of x and the variance of y are both positive, because in this formula we'd have a 0 in the denominator. So as long as they're both positive, and what do they have to do to be positive? Just a reminder, for the variance to be positive, all you have to do is have some randomness. You know, like if you had a dice that had a 4 on every face, and every time you roll it, it would come out 4. So the expected value would be 4, and the variance would be 0. We don't vary away from 4, it always comes up 4. But if there's any kind of randomness to it, if it can come out one number on one roll and another number on another roll, then the variance will be greater than 0. So as long as there's some kind of variance on both components, as long as they're both positive, and the variance is squared, so it has to be positive if it's not 0, then the correlation can be denoted by, and it's popularly used the Greek letter rho, the correlation between x and y is equal to the covariance divided by the square root of the two separate variances multiplied together. What this ends up doing is, this scales between, the covariance could be anywhere from 0 off to some number. And these two numbers multiplied together, taking the square root of it, would be equal to, would cap this at +1 or -1. So it can be shown that, and this would be a bigger computation, but if you want to, you could look this up, Google. The correlation between x and y is going to range between -1 and 1. And if the covariance of, the correlation of x and y equals 0, that means that they're not linearly connected to each other. They're pretty much independent. X and y are pretty much independent of each other. As x and y goes near +1, it means that x and y are increasingly or increase or decrease together. That would mean as one goes up, the other one goes up with it. If it went as high as 1%, then they match exactly with each other. So they increase and decrease together. And the more the correlation goes towards -1, it means that they vary inversely to each other. As x starts getting big, it causes y to start getting small. So what this will relate to is we might have two stocks that maybe one will grow. If one starts growing, then we've known in the past the other one starts growing with it. That's one that will have those two stocks will have a correlation. That correlation row will end up being something near +1. If it turns out that one stock growing causes another one to drop, if like heating stocks start going up, meaning cooling stocks, if the winter is unusually cold, that might cause some stocks to go up, which causes other stocks to go down, if their correlation is closer to -1, based on past data. Okay. And then this is kind of a side. I was thinking of adding this maybe to a third slide, but this is something that we could just use for modeling. The central limit theorem, again, this is just a refresher of probability stuff we've gone over in the past. The central limit theorem, basically, loosely put, it says the sum of a large number of independent random variables is normally distributed. So for example, suppose we took, well, the dice is more of a discrete case, but suppose we took like a distribution between 1 o'clock and 2 o'clock, where any time between 1 o'clock and 2 o'clock has an equal probability. So that would be uniformly distributed between 1 o'clock and 2 o'clock. If we then took one sample time, then another, and started adding them all together and took a weighted average, we would probably expect the average to be closer and closer to the middle. Right? If you just took one sample, it could be anywhere. Two samples, they'll average each other and be more likely to get closer to the middle. If you took many, many samples, what happens? So if we took many samples, x1, x2, and we let n go pretty large, what would happen? We would have all of these put together. What would the expected value of n samples be? If the original event has a mean of, expected value of x. Well, let's say it was what's the popular Greek letter, mu. If the expected value is mu, and you took n of them, what would you expect n of them added together? What would you expect its expected value to be? Assuming they're all independent. You expect it to be n times mu. Right? So like, for example, if the event was a dice, its expected value is 3.5. What if we rolled the dice 100 times and added up all the results? What would we expect it to be? 350. Right? They're all 3.5. You did 100 times, added it all up, that would be 350. So the expected value of this piece would be n times mu. If we then subtracted n times mu, what would the expected value of this numerator be? So if we have this event, all of these events are the same. Can I put that in? Identical. Independent random variables. Sequence of, yeah, independent and identical. So it'll be the same event going over and over, flipping a coin or rolling dice, any event. If we did it n times and we added up the total score, we would expect the expected value of this, because they are independent of each other, we would expect that the expected value would be n times whatever the mu is for this event. Whatever the expected value of each one of these individual events, multiply that by n, that's what we expect this total to be. Then if we decided to subtract n times the expected value, what is the expected value now of this numerator? 0. Because this part is expected to be n times mu, and now we're intentionally subtracting off n times mu. So now this the numerator has an expected value of 0. Could be negative, could be positive. So without this denominator, we have some new random variable, but it's no longer has the distribution of what this was originally. Now it seems to be pushing more like a bell curve towards the middle. And we've added this part intentionally just to make the expected value hit 0. Now the thing is this, what is the variance of this new thing? If they are independent, that means there's no correlation. That means the variance of n of these is equal to what? It's adding up the variances of the original ones. All right, remember last slide we said that the variance of two things added together was the variance of the first plus the variance of the second plus 2 times the covariance of the two of them. But if they're independent, the covariance of the two of them are 0. So the variance of these things added together would be n times the variance of an individual one. So we want the variance to be, we're doing this intentionally, we want it to be normally distributed. So we'll divide this by 1 standard deviation times the square root of n, which will then make the new variance of this whole thing would be 1 standard deviation. So as this gets closer and closer to infinity, as n gets closer and closer to infinity, this formula, we did the minus n to get a mean of 0, and we divided by this to get the original variance of the original individual event. This becomes like the normally distributed unit variable. So what this is basically saying is if you take a series of independent, identical events, and it could be anything, uniformly distributed, Poisson distributed, that thing we did where we had the binomial lattice, where we had it just either goes up or down, anything we do, if we run enough copies of it and just add them together, subtract off the number of copies times whatever the expected value is, we'll now have an expected value of 0. And then divide by this denominator, we would then have the same variance of the original event. What we've really done is transformed any probability distribution, if you run it enough times and add them all up, will start to turn into the normal distribution. So that's really what the central limit theorem is. It basically says that if you take any distribution is going to have an expected value, and it's going to have a variance. All of them do. If you take any random distribution and sum them up enough times and take a weighted average, it will turn into the normal distribution. So this is a powerful, it's one textbook I was reading on probability said this is the most powerful theorem in all of probability. I don't know if that's really true, but it's going to help us a lot because now we can come up with the strangest probability distribution we want and just run enough copies of it and it'll turn into the normal distribution, and we're going to use the normal distribution to model stocks.